Okay, so we start with okay, now refer to your second notes. Okay, topic 1, lecture 2 or part 2. Okay, so previously you have discussed everything about the plot, how you want to plot this graph. Okay, example 11.4-1. All right, so right here, okay, in order for you to solve a problem in example 11.4-2, okay, you need to understand these three definition. Okay, so the first one we talk about is a total reflux here. Okay, and number 2 is the minimum reflux, and the third one is the optimum reflux ratio. Okay, just want to recap a bit. Okay, what is the meaning of this reflux? So you know that if you have a continuous distillation column, okay, you have a feed. So at the bottom part, usually we're going to install a condenser. Okay, so the vapor coming out from them, okay, to the top part of this column, okay, will condense and change into the liquid phase. Okay, so you know that part of it, okay, will go as a distillate stream, we label as a D, and part of it will recycle back into the column. So usually we label this one as a L or the SL. So since we assume that the system inside here is the equimolar condition, so you know that this L is equal to Ln. That will give you the ratio, okay, supposed to be L over D, which is how much you recover, sorry, how much you send back to the column over how much that you recovered. So R is equal to L over D, which is also equal to Ln over D. So if you go back here, okay, what is actually the meaning of the total reflux? Okay, so this is the brief definition of the total reflux, which is the returning all the overhead condensed vapor V from the top of the tower back to the tower as reflux. So if you can imagine that if you have a feed stream coming into the column, okay, so some part of it will go to the top part as a vapor, and you condense it back into the liquid. But right here, all the liquid is sent back to the column. Okay, so means here in the case of total reflux, there is no recovery of product inside the D stream. Okay, so so that the limiting values of the reflux ratio R is equal to infinity since D is equal to 0. So R, you know, ln bahagi 0, ln you divided by 0, it will give you infinity, which means that the number of ln will be very large. So same thing goes to the vapor Vm, because all the liquid, okay, is sending back to inside the column. Okay, so if that case happen, okay, that the slope of enriching and stripping operating line, okay, will coincide with 45-degree line. So if you still remember a typical look of this graph, okay, y over x, you have a 45-degree line, and you have a curve, right, for the equilibrium. So usually you know that your enriching line is somewhere here, for example, and your stripping line is somewhere here. But for this case, okay, your stripping line and enriching line, okay, will overlap with the 45-degree line. Okay, will overlap with the 45-degree line. So if you want to calculate, okay, the number of stages, okay, you just simply need to have the 45-degree line and also the equilibrium line, and you can see that the number of tray required is minimum. Okay, if you compare with the example 11.4-1 that we have discussed last Wednesday, okay, so you can see that if we eliminate the if we do the calculation of n, okay, between the 45-degree line and equilibrium line, that will only give you approximately about maybe n is equal to 3.8. Okay, however, for this case, okay, even though that the total number of thread is minimum, but the tower diameter will be very large. Okay, so this is also corresponding to a increasing of the cost of the tower as well as the steam and the cooling water. Okay, so even though that you can save the cost by reducing the number of stages required, but it's also not possible in a real chemical industry because it will cost you increase the cost in terms of the diameter. Okay, however, in order for us to calculate what is the minimum stages required for that particular system, okay, so this is the equation that you will use. Okay, so you remember that this SD is the mole fraction of liquid coming from the top part, and you have the XW, okay, coming from the bottom you have W and also the XW, and then you have this alpha. Okay, so alpha here refer to the relative volatility. Okay, this one I should cover during the, the second part of our lecture during the first week, but I still didn't make a new video for that. Okay, but maybe I just briefly explain here. Okay, what is the meaning of relative volatility of a mixture? Okay, so usually we calculate first. If you have example benzene and toluene system, okay, so it means that you refer this benzene as component A, toluene as component B. So we need to calculate as alpha AB. Is that is refer to the relative volatility of components A and B. So this calculation of alpha, right? Alpha is actually a numerical measurement on how easy the separation. Okay, how easy the separation. Okay, so if you get the alpha value is bigger than 1, means that the separation process for that particular component is possible. All right, so this is a definition of the alpha. So alpha AB is equal to this one, and okay, after certain derivation we come up with the conclusion that okay, alpha AB is equal to PA over PB. So I hope you still remember that this PA, capital P here, refer to the vapor pressure of A, and this one is referred to the vapor pressure of B. Okay, so that's about the relative volatility. What is the definition? So you know alpha AB is PA over PB. All right, now go back to here. So in order for you to calculate for N minimum, okay, so for the XD and SW, so here you have the alpha average is equal to alpha, I cannot see, alpha 1 or L, I'm not sure, alpha W to the power of half. Okay, so this alpha 1 is a relative volatility of overheat vapor. Okay, means that here, okay, vapor, you need to know what is the value of your partial pressure of A and partial pressure of B, and that's referred to the alpha 1. Let's say alpha 1 is equal to PA over PB. So at the bottom part, alpha W, okay, you need to know what is the partial pressure of A and partial PB, vapor pressure of PB respectively. Only that you can calculate for alpha average, and eventually you can calculate for the NM. So here M here is referred to the minimum. So you know that when you talk about a total reflux, okay, total reflux will give you a condition of minimum stages. Okay, so when you're talking about total reflux, means that you can calculate for a minimum stages. What is the minimum stages required for that particular system? All right, and that for the first case. So the second one is a minimum reflux ratio. Okay, the first one is total, so the second one is minimum, whereby that I think that the case is somehow terbalik dengan the first case. Okay, so let's imagine that you have a system, okay, and you have a feed coming in, and then it will change the vapor, the light boiling point components will change it into vapor, will cover inside the condenser. So if the total reflux, all the liquid phase will turn back into the column. But for the case of minimum reflux, okay, most of the liquid will go to the distillate stream. Okay, we'll go to the D stream. Only minimum vapor flow from the top of the tower, which change into the liquid, will go to the liquid stream. All right, so if you can see that the case number 2 is somehow favorable, because when we because we want to recover the product, right, by using the distillation column. So getting as much as the product from this distillate stream is favorable lah, is desired. Okay, however, for this case, okay, if R is decreased, the slope of enriching and operating line, okay, will move farther from 45-degree line and closer to the equilibrium line. Okay, so if this case of total reflux, the enriching and operating line will approaching the 45-degree line and overlap to each other. And for the case of minimum reflux, R min, so you know dia akan terbalik dengan case yang pertama tadi. Of course, the enriching and this stripping line here, dia akan menjauhi 45-degree line as much as possible. Alright. Until that these two operating line touch the equilibrium line. Okay, so there is here what we call as a pinch point. Okay, so the pinch point later during your part 5, I think when you take process integration, okay, we'll recall us, or you will discuss later, okay, what is the meaning of this pinch point, okay, what is the effect. So this at this pinch point, okay, you will have the X prime and Y prime. Okay, now yeah, so if you look up here, okay, if the operating line, both operating line move further from the 45-degree line, okay, so you can see that the number of stages will be maximum. Okay, the number of stages will be bigger than if you have an ordinary case like the example 11.4-1. Okay, so as a result, the total number of tree is increased, and that will also correspond to the increased cost of tower. Okay, so that's what, okay, how to calculate the minimum reflux ratio RM here. So this is how it goes. All right, this is the equation. So RM here over RM plus 1. So you know this XD refer to the components composition at the distillate stream, and Y prime S prime, okay, you can find that value from the pinch point, okay, on your graph paper. Okay, so since that both first two cases, total reflux and minimum reflux, not favorable because of that cost. All right, so that's why in order for us to design a distillation column, okay, we need to find the optimum reflux ratio. Okay, not a minimum, not a N minimum, and also not the R minimum. Okay, now you read here, for the case of total flux, the number of plate is minimum, but the diameter is infinity. The diameter is too big, and that will increase the cost of the tower. That's for the NM. However, for the minimal reflux, okay, the number of tray is increased. Okay, that will also give you the increase, will cause an increased cost. All right, will increase the cost. Okay, so these are the two limits in operation and operation of the tower. So usually the actual reflux ratio is to use is like between these two limits. So this kind of thing, okay, usually the assessment, okay, coming out in term of the question, your knowledge and understanding. Okay, soalan C1 dengan C2. Alright, C1 and C2, test your knowledge and understanding. Alright, so that's why in many cases, okay, stated here, operating reflux ratio is between 1.2 RM and 1.5 RM. Okay, this thing is what we call as a rule of thumb for chemical engineer. In fact, there is a book okay, rule of thumb in chemical engineering means that what is the practical the practice inside the actual chemical plant, because what we have learned before inside the class is it's all about the theory, but when we come up with a real design, okay, there is a lot of factor, okay, that we need to include, and usually the operation is an unsteady state, okay, we cannot make an assumption there is no heat loss and everything. So that's why usually in designing this distillation column, okay, you need to calculate for the RM. So your optimum, okay, the rule of thumb for the R optimum is bigger than 1.2 R minimum and must be less than 1.5 R minimum. Okay, so that's why let's say that after this inside your assessment that you need to have a problem to solve, okay. So kalau soalan biasa kalau sebelum ni, okay, dalam non face to face closed book examination or closed book assessment, usually it will be the question is exact, means that your calculate for R minimum and take your optimum condition as 1.2 R minimum. But for this time being, okay, since we have the ODL classes, okay, it means that even though that the R is not given, okay, your R value is not given, means that you need to know that, okay, first of all, I need to calculate for the R minimum, okay, and then you need to decide, okay, let's say that our system is 1.2, R is equal to 1.2 R minimum, okay. So that's why during your assessment, usually the answer script between each group might be different. Dia takkan sama because different group will refer to a different chart, maybe different sources and also different assumption. And sama juga nanti waktu you buat plan design project when you are in part 7 and 8, same thing goes to your project. Okay, you are the one who need to make a decision. So this thing you need to recall back lah. Okay, what is the rule of thumb in finding the R reflux ratio. Okay, first one calculate for RM. So this is the one of the rule of thumb for the chemical engineer. All right. So now, okay. So look out into example 11.4-2. Okay, this example is actually a continuity from the previous example that we have discussed last Wednesday. So why don't you flip your book and read this question first. Okay, sorry tadi saya punya line terputus. Alright, so I hope that you can see my slide and hear my voice clearly. All right, now we go to the example 11.4-2. Okay, so right now this question is a continuity from a previous example. Okay, we are talking about a benzene and toluene feed is being distilled to give a distillate composition of XD 0.65. Okay, so you know that from the previous one, right? You have and then XD is equal to 0.95 and XW is equal to 0.1. All right, so what is the minimum reflux ratio? So this is the equation that we're gonna use. Okay, Rm over Rm plus 1 is equal to Sd minus y prime and s prime. So you know that this y prime and s prime is the pinch point. So Sd you know, which is 0.95. Okay, so the y prime and s prime here, okay, is actually the intercept. All right, okay, you have the enriching operating line for Rm here from XD at 45 degrees Celsius. You bring it to the intercept line between Q line and equilibrium line. Okay, and the intercept between the Q line and VLE, okay, vapor liquid equilibrium, you read the you look out into the X prime and Y prime value. Okay, so I hope that previous example you done the plotting, okay, graph plotting properly. So here you should get the value of X prime. Okay, I'm not doing it, but I'm looking inside the book, but I hope that you get the same value, okay, approximately. Okay, more or less, kalau lari sikit pun tak apa. X prime is 0.49 and y prime is 0.702. So directly put this equation inside here and look up if you get this Rm, okay, minimum reflux ratio should be 1.17. Okay, this is your answer. Kelas saya kena stop sekejap.
Okay, doktor.
Okay, sambung. Next question is you need to calculate for a N minimum. Okay, so you know that N minimum is the case of the total reflux, whereby the enriching and the stripping line is overlap on the 45 degrees Celsius. Okay, so imagine that if you have plotting y and x, okay, and then you have 45 degree line and you have the equilibrium line. So you no need for you to plot enriching and stripping line, because you know that that line will overlap on a 45 degree line. So with this, okay, you try to calculate what is the number of stages required. So if you look out here, okay, from this graph, um, the total will give you 5.8. Okay, so means that is equal to 4.8 stages plus reboiler. Okay, so that's the case of the R minimum and also the N minimum. Okay, so any questions so far before we end our class not our class, our topic of the total reflux today? Because after this we want to look into topic 1 part 3. Okay, which is, if you look out into the lesson plans, we want to focus on this. We are actually cover 1.51, 1.52, 1.53. Okay, but for now we want to go back to the 1.5.2. We want to look out how is actually the method of Lewis-Serrel for calculating the number of stages N and also the location of the fit tree. Okey, ada soalan tak untuk yang ni? Okey, kalau tak ada soalan, check out your lecture 3. Okay, now we go to the lecture 3. Okay, we talk about rectification and continuous distillation. Okay, the same thing. But right now we want to use the Lewis-Serrel method. Okay, so if you notice, this method is it's not covered inside the our main textbook, which is the Gin Corpus. If you look into the lesson plan, okay, this part, okay, so this is the main textbook that we're going to use, which is the Gin Corpus. However, we have another alternative, okay, for different books that you can refer, Metcalfe, Tribal, and so on. All right, I'm still not figure out, okay, this Lewis-Serrel method coming from which part of this book. Okay, so for today class, we just rely on this note. Okay, for to understand what is the Lewis-Serrel method and also the example given later. Okay, so nantilah next week kalau saya jumpa the sources of this note, and then barulah kita boleh tengok contoh lain daripada untuk Lewis-Serrel method ni. Okay, now okay, for this method, okay, stated here that the feed stream is introduced. The feed stream is introduced on some intermediate train. Okay, so before that, you know that the distillation column. Okay, so same thing with the Metcalfe. Until when we talk about continuous distillation, you're gonna have this thing. Okay, reboiler and condenser. All right, so for this particular part, okay, the top part, okay, you refer as the rectifying section. Okay, dia just beza sikit je lah. Kalau sebelum ni kita panggil enriching, but it's just the same thing. And the lower part we call as a stripping section. Okay, so the concept of this method the feed, okay, is introduced where the liquid, okay, has approximately the same composition as the feed. Okay, so you have a multiple of stages here, okay, a multiple of n, so different n will give you different composition, okay, of y and x. Okay, this y x different with this y and x. So at certain stages, okay, the composition of A in liquid, okay, will be similar, more or less similar with this SF. Okay, so that's the location of the feed stream. Okay, we want to introduce the feed stream at the location where the liquid has approximately the same composition as the feed. Okay, so with constant molar overflow assumption again, so you know that when you want to do a mass balance for a distillation column, okay, you so familiar, right? If you want to have mass balance around the n stages, and that refer to n, so atas dia n plus 1 and bawah dia n minus 1. Okay, but we assume that we constant molar overflow assumption, okay, so that this L n minus 1 is equal to Ln is equal to Ln plus 1 and so on. Same thing goes to the vapor molar flow rate. Okay, so this is some assumption, okay, some condition for this constant molar overflow. How can we actually assume this thing to happen? Okay, so we assume that because there is no heat losses, okay, output, no, actually, of course, in a real life, okay, there is a heat losses throughout the column, but we just neglect it, okay, so the heat loss is negligible, and then we neglect the heat, okay, of mixing. And then we also assume that the equal or close heat of vaporization. Okay, so this is certain assumption, all right. And then okay, four streams are involved in the transfer of heat and material across a plate as shown in figure above. Okay, I think figure below here. Okay, this is not clear. Okay, but I think you can zoom in inside your notes. Inside your notes, I think you can zoom in. Okay, so this one is FSF. You have DXD. All right, so plate and receive liquid Ln and plus from, okay, this time I think as I mentioned before, if you have n, this one is n plus 1, and you have this n minus 1. So if the vapor, okay, coming from the n minus 1, and you need to label as v n minus 1. All right, so if the L is coming to Ln, okay, from n plus 1, then you label as Ln plus 1. Okay, so if you want to have this overall mass balance, then you know that Vn minus 1 is equal to Ln plus 1. Okay, that's how we write mass balance inside the distillation column. All right. Okay, action of the plate is to bring about mixing. Okay, so that the vapor Vn will mix with the liquid so that it will reach equilibrium. So in this case of a Lewis-Sorel method, okay, when the composition reach equilibrium, okay, as the vapor and liquid mix and reach equilibrium, okay, you will have this term prime here, okay, Vn prime, Yn prime. So Ln prime and Sm prime. So you know that when you see this kind of prime, you know that the system is in equilibrium. All right, now next we go to the this figure. Okay, so this is the original one. So you know that we have the feed coming in, okay, and SF, I think it's just similar with the MATCAP and TIL method. You have feed and SF, and then you have a D and SD, and also at the bottom part you have a W and SW. All right, so for Lewis-Sorel method, you also need to develop the operating line equation. So the first operating line is developed on this border. Okay, border yang kat atas ni, dash line here. So the second operating line is developed at the bottom part of the column here. So if you can see here, okay, that you have stages N and you have N. And I mentioned earlier, the liquid coming from the liquid coming to the N stages we label as Ln plus 1, so that the V coming from N we call as a Vn. Okay, so everything deal with the rectification section, okay, we label as N. So untuk top part, untuk bottom part we label as M. Alright. So this one, okay, the exact same figure. Okay, configure binary is this to give top product. Okay, the vapor VT rising from the top peak. Okay, so here we have a level VT here. Okay, so VT here means refer to the total vapor from the column. Okay, so you have the VT and of course you have the XT or YT. So usually the XT is equal to 0 because everything is changed into the vapor, and YT is equal to 1 here. All right, we have the VT here. So part is run back as liquid as boiling point to the column as reflux remain withdrawn as the product. All right, now we go to the first operating line. Okay, now focus on the first border. Okay, first dash line here. So if you look out here, stated, okay, Bn is equal to Ln plus 1 plus D. Okay, the coming in is equal to stream coming out. Okay, just easy. So when you want to, this is the overall. Okay, overall. So when you want to plot, when you want to write a component balance, just multiply that overall with the component balance. So Yn Vn is equal to Ln plus 1 Sn plus 1 plus DSD. Okay, so in order for you to have a straight line here, just bring the Vn to the right hand side. Y is equal to Ms plus C. All right, and then you know that we assume that the system is in equimolar overflow, so you know that the Ln is equal to Ln minus 1 equal to Ln plus 1. So you can just replace the Ln plus 1 here with Ln. That will give you much simpler equation, and here you label as equation 6. I don't know why equation 6, maybe inside the books there is actually a continuity from another equation. Okay, nevertheless, we just follow the notes. Okay, this is the equation 6, and this is represent the operating at top column. Okay, operating line at the top column. Okay, now we go to the second equation. Okay, if this one is the top column, so the equation 7 must be the operating line at the bottom part. Sekejap kelas. Okay, so now we go to the second second operating line. Okay, so right now you need to focus at the bottom part. Bottom part. Okay, if you look here, okay, Ln plus 1 is equal to Vm plus W. Okay, in is equal to out. Okay, Ln plus 1 is equal to Vm plus W. So when you make an arrangement, so Lm is equal to Vm. Betul ke? Sekejap. Lm plus 1 is equal to Vm plus W. So Lm, okay, betul lah. Alright. Okay, so Lm is equal to Vm plus W. Okay, so you know that because Lm is equal to Lm plus 1. Alright, so you just multiply with the components balance and rearrange, and then you get the equation 7. Okay, Ln Vm multiplied by Xm plus 1. Okay. Okay, so now you have two equation, two operating lines. So in order for us to solve for this, to solve by using the approach of Lewis-Sorrell method, we still need to have the equilibrium data. All right. Okay. So right now, now we go straight away go to the example. Okay, we still using the same binary composite fluid. And this approach, okay, also require you to have equilibrium data. So I think you need to plot a new graph because I think your previous graph will be so mess. Okay, so just plot y versus x right now, a new graph. Okay, I want you to have a new graph paper for this method. Okay, now plot a 45-degree line and also a new equilibrium line. Okay, for benzene and toluene. Buat yang baru lah, jangan ambil yang sebelum ni. Okay, read the question sambil plot tu. Okay, a mixture of benzene and toluene containing 40%. Okay, let's see. The feed is heated so that it enters the column at its boiling point. Okay, boiling point. And the vapor leaving the column, okay, is condensed. So all vapor is condensed. And you know that T feed is equal to T boiling point. Okay, so no need for you to find the T boiling point. It is proposed to operate, the unit value flow ratio is equal to 3. Right now, generated position find stages. Location of feed 3. Okay. The equivalent data. Okay, so equivalent data ni you can take from the previous example sama je. Okay, the one that you used, the data that you used to plot the curve tu. Okay, now we go to the how we're gonna solve this problem. Okay, by using the Lewis-Sorrell method. Okay, the first one you need to solve for a overall material balance. So I think this one should be a problem. Okay, okay, since the feed molar rate of feed is not given, so we take the basis of 100 kilogram mole. Okay, k-mole. So you know that F is equal to D plus W. This is easy. So that will give you W is equal to 100 minus D. Okay, this one is easy. So you do the component balance. Okay, I think this one is easy. Okay, so by right, you get the value of D and W. Right. So we'll solve it. Okay, tengok dapat tak the D and the value of D 37.5 and W 66.5. Okay, so should be a problem, right, to solve this overall and component mass balance. Okay, now we recall the definition of R. Okay, as I told you before, R is equal to ln over D, and eventually you know the value of R. Okay, and the D distillate you just calculate it here. Okay, and that will give you your ln is equal to 112.5 kilogram per second. Okay, so this is your value of ln. So right now you have the value of ln. Okay, now look into the from material balance at the top stage. Okay, at the top stage here. Okay, this one. Vn is equal to ln plus 1 plus d. But you know that the ln plus 1 is also equal to ln. That will give you Vn is equal to ln plus d. Okay, Vn is equal to ln plus d. You know the value of ln and d, so you know the value of Vn. Okay, so right now, we need this information because we want to solve for a first operating line equation, right? So recall inside the notes, Yn is equal to ln over Vn. Okay, you got the value plus d over Vn. So eventually you will get this first equation for operating line. Yn is equal to 0.75 Sn plus 1 plus 0.225. Okay, equation number 1. Okay, now we go to number of plates by Lewis-Sorrell. Now we go to the second operating line. Okay, we want to evaluate the second operating line. Okay, so it's stated here, since the feed is all liquid at its boiling point, it will run down as increased reflux to the plate below. Okay, so in case of this Lewis-Sorrell method here, okay, let's say that you have a feed, right? Okay, this dashed line is referred to the feed, location of the feed point. So whatever above this feed line is what we call as label SN. Okay, apa yang kat bawah we label SM. So coming into M stages, okay, is we label as LM. Coming into the N stages, we label as LN. So if we make a mass balance, okay, mass balance at this border, okay, feed here. So we can see here the coming in is F plus LN, okay, is equal to LM, okay, the one that going out to the bottom part. So by looking at this correlation, okay, you know that the LM is equal to liquid flow coming from the rectification section plus the feed. All right, so you have Ln and F, so you know what is the liquid move downward to the bottom part. Okay, so if you look out into from a material balance at the bottom, okay, so we know that the Vm is equal to Lm minus W, so we can calculate for a Vm. So we know the value of Lm and Vm. So in order for you to have this second line, second operating line, just put it inside this equation. So eventually you will get Ym. This one is Yn, right? N is on the rectification section. So here Ym refer to the stripping section. So you should get these two equations so far. Okay, the first one and the second one. Okay, now from these two equations, okay, 1 and 2, okay, we're going to calculate the composition on the various feed, okay, and from that we should determine the location of the feed stages. So how we going to do that is, okay, panjang lagi ke? Right, skip. Okay, since all vapor from column is condensed and the composition of YT from the top plate is equal to the SD and the return. Okay, so here, if you look up, if you recall here, okay, so okay, in this case, they label this one as the SR, okay, bukan SL, but it's just the same thing, okay. So since that the all vapor is condensed, okay, so you know that the composition of the AYT is equal to SD and must be equal to SR. Okay, so okay, how are we going to use this equation? Okay, you already developed the first and second equation. All right, so let's really quick. Okay, from the first equation, okay, right now we want to calculate the composition from the top. Okay, now take the first equation. Yn is equal to 0.75 Sn plus 1 plus 0.225. Okay, okay, now let here let YT, okay, is equal to 0.9. Okay, let YT is equal, sorry, I'm lost. Okay, sorry. Let's say N plus 1 is equal to SD. Okay, so first we start here. We start here by taking the value of Sn plus 1 here is similar with the SD. Okay, so when you put the value of SD, 0.9 inside this equation, that will give you the value of Yn, which is 0.9. Okay, 0.9. So what you're going to do after you have this value 0.9, okay, just now I'm asking you to plot the graph, right? So now you have this graph, okay, y versus x. Okay, so you have 0.9, okay, you bring it to the equilibrium curve here and bring it to the x-axis, and you need to read what is the value of xt. So from here, okay, I hope you do it by yourself lah. Okay, xt is equal to 0.79. Okay, don't rely on this figure. Okay, buat sendiri. And let's see, did you get the value of 0.79? Okay, so at yt 0.9, it will give you the xt 0.79. Okay, so first of all, start with the value of xd. This value of xd will give you the value of yn, and this value of yn will give you the value of xt. Okay, so yt 0.9, xt 0.79. Okay, that's for the first tray. Okay, so what about the value of yt minus 1? Means that the location of this tray, okay, or the composition is one step behind, below the tray t. Okay, t minus 1. Okay, now you take the value of 0.79 here. Okay, take the value of x, put it inside the equation. Okay, and you will get the value of yt minus 1, 0.8175. Okay, by logic, your value of vapor composition should be less than 0.9. Okay, sebab if you imagine inside the tower column, right, as the vapor goes in, of course that it will be richer in vapor phase. Sampailah ke atas ni akan totally vapor. So that's why Vt is equal to 1 sometimes. Okay, so if you are talking about, okay, tapi sini di case dia Vt is equal to, for example, 0.9. So if you want to calculate Vt minus 1, of course that the Vt minus 1 must be less than 0.9, because the composition of vapor will increase as they go upward. Alright, so now you repeat the same step. After you get the value of 0.8175, then 8175 here, go through this equilibrium line and read what is the value of the xt minus 1. And that should give you 0.644. Okay, huh? That should give you somewhere here is 0.644. Mana saya terlost again here? Okay, now I give you about 5 to 10 minutes. Can you? Okay, now you are here, right? So can you repeat the step for t minus 2 and t minus 3? Okay, can you repeat this first step before I continue to explain on this t minus 3? Okay, boleh ke? I hope shouldn't be a problem, okay, untuk step untuk dapatkan 0.492, okay, then again put the value inside the equation, and okay, you get the new value, the composition at t minus 3 is equal to 0.382. Okay, so if you recall back the first definition of this Lewis-Sorrell method, okay, the first step here is stated here that the feed stream is introduced on some intermediate tray, okay, the tray, some intermediate tray here, where the liquid has approximately the same composition as the feed, okay. So if you look back to the question, the SF is equal to 0.4. So after you done some calculation, okay, and then you find out that at T minus 3, okay, the composition is 0.382, which is approximately more or less similar to 0.4, which is the X fit. Okay, so you know that the last value composition is sufficiently near, okay, to the fit composition, so that we know that from this method, okay, fit is to be introduced on the peak T minus 3. Okay, 3 step below the top 3. Okay, all right, so means here, after that you discover that this is the fit plate, you need to stop to use the first equation, which is on the top part. Okay, now you need to take a second equation here. Okay, so the first one, you for the first step tadi kita guna equation pertama, right? So after you find out, okay, that the fit is occur at t minus 3, then you, after that you need to start the second equation, which is the ym. Okay, okay, now, so to calculate t minus 4, okay, because you know that the fit is t minus 3, you take a bottom operating line. Okay, so ym is equal to 1.417 sm plus 1. Okay, and then you just same thing like before, okay, take the value of previous x 0.382, put it inside the equation. Only that right now the equation is bottom operating line. Okay, then you will get the yt minus 4 is 0.5. And then look out into the equilibrium line, and you will get the value of xt minus 4 is equal to 0.298. Okay, all right, so similar step, and okay, so this is for 3t minus 5. We'll get the t minus 5, 0.280. Okay, you have t minus 6, you have 0.120, and you have t minus 7. All right, so why you should stop now, because you can see that at t minus 7 is already equal to 0.048. Okay, so approximately 0.05. Okay, so if you look into the question here, the XW, all right, the SW coming out from the reboiler is the 0.1. So if you have the value of 0.05, which is less than 0.1, it should maybe the value of x minus 7 here is corresponding to the value outside the reboiler. Okay, so there will be 7 plate in the column, so you calculate one top, okay, 1 2 3 4 5 6 7. Okay, so this yt is referred to the top, so yt plus 1, so 1 plus 1 until plus 7, right? So you have 7 stages, okay, 7 plates. And as usual, you know that these 7 stages including the reboiler, so totally you have actually 6 stages plus 1 reboiler. Okay, so by end of this class, okay, patutnya sampai up to this point, okay, you should have this your first diagram to represent the calculating the number of stages by using the approach of Lewis-Sorrell method. Alright, now you have any question so far regarding this Lewis-Sorrell method? Yang tak faham ke? Okay ke setakat ni? questions so far? Okay semua. Alright, so kalau tak ada soalan, I think we should take a break, okay, for 10 minutes. Alright, so maybe you should, we're gonna have maybe around 50 minutes tutorial. I think my was ready. Okay, so maybe we have 10 minutes break. Okay, kita akan sambung 11.30 nanti. And before that, maybe we just should flip. Okay, so far what we have learned today. And I mean what we have learned for this week. Okay, so nanti kalau tak ada apa-apa, kita 11.30 we will start our tutorial class. Just a simple one. Okay, I just write down maybe several steps for certain problem. Okay, okay ke? Sekejap je.
Okay, doktor.
Okay, doktor.
Okay, sama 11.30 nanti Okay, class. So we should continue. Okay, our lesson today on tutorial. Okay, all right. Now, okay, I've already write it down. The problem. Okay, by right up to this point, you should be able to solve problem 11.4-1 and problem 11.4-2. So this question, okay, both you need to find the number of stages and also the location of the feed tray by using the approach of McCap and tail. Okay, and then continuing straight with the problem 11.4-3 and 11.4-4 for reflux ratio. Alright, so for the Lewis-Sorrell method, I try to find the sources of the nodes first. So maybe I can find another example for the Lewis-Sorrell method later on. Okay, so right now go to your book, okay, and look out into a problem 11.4-1. Okay, a rectification column is fed at 100 kilogram per mole. Okay, it's fed over 100 kilogram mole per hour. Mixture of benzene and toluene. Okay, we still talk about the same system, benzene and toluene. So right now the mole fraction is 0.5. So the operating condition is 1.32 kPa. The feed is liquid at the boiling point, so TF is equal to dBp. Still contains 0. So the reflux ratio is 1.52. So right now the question asks you to calculate the distillate. Bottom and number of three. Okay, so this question is exactly similar with the example 11.4-1, only there is a change on the components and on the composition and also on how you're going to draw the Q line. Okay, so let's do this step by step. Okay, first you need to solve for the overall mass balance, right? I think it's just easy. Okay, F is equal to D plus W. So you will get the 100 is D plus W. Now you have component balance. Okay, so from here you can solve for D, and after that you can solve for W, which is still 100 minus D. Okay, now go to the next question. Okay, we want to number of theoretical stages. Okay, the first one, I just write down the step, so maybe you can try it by yourself. Plot equilibrium line. Okay, so we are talking about the same system, which is benzene and toluene. So by right, you can refer to the same table as table 11.1-1 because the pressure is also at the atmospheric pressure here. Okay, now we go to step number 2. You need to write down the enriching operating line. Okay, so if you recall, I'll flip the notes. Yn plus 1 is equal to r plus 1 Sm d r plus 1. So the equation is very direct because r, you know, is equal to 4.52. Your Sd is equal to 0.9. So you can eventually solve the operating line. Okay, so if you still remember, you need to first plot a graph, right? Okay, of the y versus x. Okay, and you have a 45-degree line and you have the equilibrium. All right, so after that, after you get this enriching operating line, okay, you need to have 2 points, okay, of x and y, 2 points to plot a straight line. All right. Right, so after that, you need to plot a Q line. But this one is so special because doesn't need to have any calculation of the Q line, because if you read the question carefully, okay, so the feed is liquid at the boiling point. So what happened to the Q line when the liquid is fit to the at the boiling point? So I want to just you refer to the notes, okay. So but this case will be much simpler compared to the example 11.4-1 that we have discussed before. Okay, how to draw the Q line for this case, you refer to the notes, okay, for this specific condition. Okay, after that, you have 1, 2, 3, 4 lines right now, 45-degree line, VLE line, enriching operating line, and Q line. So you know that for the stripping line, okay, you can just draw from the XW here, okay, so a point of XW on 45-degree line, you make it a straight line to intercept, okay, between Q line and enriching line. All right, and after that, okay, so far there's any question? Tak faham ke dengan step yang saya tulis ni? We can straight away calculate the number of trays needed. Okay, so you know that for the location of feed stream, okay, after you have that Q, okay, you bring that Q perpendicular, okay, that will give you the location of your feed tray. All right, so I just write down the step here. So I hope that shouldn't be a problem for you, okay, to solve this 11.4-1. Okay, and I think for the 11.4-2 pun benda yang sama juga, but you are talking about a different system. Okay, for problem 11.4-2. Okay, kita tinggal sekejap 11.4-1 here. Okay, okay, by right, if you look out inside the books, okay, the answer for D is actually 50 kilogram mole per hour. The W is also 50 kilogram mole per hour. Okay, so here 4.9 theoretical stage plus reboiler. Okay, so your N should be 44.9. theoretical stages plus reboiler. Okay, so I want you to do this, okay, by your own. Okay, try to do this, to do this, okay, and see. Let's see if you get the exact same answer with the one that given to you inside the book. All right, now for the 11.2. Okay, I think just read the question. I hope I think saturated liquid feed off 200 mole per hour at the boiling point. So the same thing goes to 11.4-2. Okay, for this one, in order for you to plot this Q line, okay, so you should refer to note. Okay, what is the meaning? What kind of Q line that you will plot when you have a saturated liquid feed at its boiling point? Okay, so F is given. Okay, the value of S is given. The SF is also given. Okay, and as usual, the value of SD and SW is also given. And the reflux ratio is given equal to 2.5. All right, so calculate the same things. Okay, calculate WD and number of stages. So right now the equilibrium data is given just after the question. Okay, so you can see here the value of X and Y is given. So you just repeat the same thing. Okay, plot the equilibrium line and everything. Alright, so right now, after you solve this problem, okay, 11.4-1 and 11.4-2, okay, if you look out into the 11.4-3, it's actually correlated with 11.4-1 here, okay, it's just a continuity from this question, okay, so what you just, I think, you consume less time to solve this one because you already have the graph, you already plot the graph, so you can just straight away try to solve this problem by using the same graph. Okay, and same thing, 11.4-4 is a continuity. Okay, is continuity from the problem 11.4-2. I think that the question is straightforward. Okay, so I hope you can just do it by yourself first. Okay, should you have any question, okay, tak faham ke apa ke, then we can discuss on the next class. Okay, I will see you on your class 4M, okay, Wednesday. Okay, so I plan to have, since dah start puasa that time, okay, I plan to have a what we call a synchronous class. All right, next Wednesday maybe I should record and we should start a topic on the trade efficiency. But I think okay, tak apalah macam ni lah, apa-apa pun I will inform you after this. Saya nak buat kelas macam mana, you just stand by. Okay, so tiba-tiba saya datang mood nak buat kelas online, then kena stand by jugalah hari Rabu tu pukul 10 pagi, and then maybe the class on Friday that we're gonna have a asynchronous mode. Okay, so if there's no question, I want to end this class for today. So any last question? Tak ada persoalan? Tak faham? Untuk kelas hari ini? Ada tak?
So
Tak ada.
rasanya tak ada betul.
Tak ada. So cuba dulu buat dulu. Kalau boleh buat tu insyaAllah faham lah tu. Okay, so I want to end this class. So I want to say thank you for your attendance and attention. So good luck. Alright. And selamat berpuasa. Assalamualaikum.
Waalaikumsalam. Thank you, doktor.
Thank you, Becca.
Thank you, Doktor.
Thank you, Doctor.
Selamat puasa, doktor.
Okay, selamat puasa.
Thank you, Doctor.
Selamat puasa, Doktor.
Doktor.